Hello YouTube. The other day in the lab I was thinking, what if I had a resistor? What if I wanted to dissipate a certain amount of power in that resistor? Let's assume I only have an AC signal source. So I could do it that way, but that would be way too easy. So let's select a more challenging approach. Yeah, that looks good. But right after that, a question came to my mind. Which phase angle would be needed in order to dissipate exactly 18% of the maximum power in that resistor? Well, as it turned out, this simple question brought me all the way from theory to software development to hardware development. And if you like, please feel free to join me on this little adventure. First of all, let's start with our sinusoidal AC power supply. If we now, after each zero crossing, trigger the TRIAC gate delayed by a certain amount of time we define as alpha, this will result in the following voltage across our resistor. Of course, applying a voltage of any shape to a pure resistive load will always result in a similar shaped current with an amplitude only determined by the resistor's value. However, since we are applying a sinusoidal shaped voltage to our resistor and running a current in a sinusoidal shape through our resistor, we will dissipate a power that is proportional to a sine squared waveform. So the only thing we need to do in order to control the average power or energy that will be dissipated in our resistor is to trigger the TRIAC gate after each zero crossing delayed by a certain value of alpha. It can be easily figured out that there is a relation between alpha and the output power. The higher the alpha value, the lower the average output power. The lower the alpha value, the higher the average output power. But it would be great having a mathematical formula describing this relation in detail. So let's dig deeper. The instantaneous power P of t is given by the instantaneous voltage U of t times the instantaneous current I of t. The instantaneous voltage, on the other hand, equals our voltage amplitude times sine omega t. Since generally current can be expressed as voltage divided by resistance, our instantaneous current can be calculated as our instantaneous voltage divided by our resistance, which is in the end our voltage amplitude times sine omega t divided by our resistor value. If we now insert the two equations for voltage and current into our first equation, we end up in a pretty handy formula to calculate our instantaneous power. Since we are not interested in the instantaneous power, but in the effective power, we need to integrate over the instantaneous power waveform. This brings us to the following integral. Let's also add alpha to the integral. This results in two integrals, one for each half wave. Both integrals result in the same value, so let's cancel one out with the 2 in the denominator. Now the equation looks as follows. Let's solve the integral. Our result still contains the peak power, which we need to get rid of. Let's find our maximum effective power value and define it as 100%. Now we've got a normalized equation for an effective power as a function of alpha. Great! Now let's do some quick tests on this formula. A first good test value is pi over 2, because this value would result in the following waveform. As you can see, exactly half of the possible area is covered. So we would also expect an output power of exactly 50%. Inserting pi over 2 into our formula confirms that. Very good, let's go to the next one. Another good test value is 0, because this results in a pure sinusoidal full wave, which definitely should give us 100% output power. Let's do the check. Okay, that's also correct. Finally, we set alpha to pi and check the other side of the rainbow. We then get a flat line, and this voltage waveform should not produce any output power at all. Let's do the check. Well, also this result seems to be correct. Although we didn't test every possible value, which we couldn't do by the way, it looks as if we found a valid equation that can calculate the normalized power as a function of alpha. But wait, didn't we want to find an equation that does the job the other way around? Well, as it turns out, there is no such function, since no reverse function of p of alpha exists. If you can prove me wrong, and there is a reverse function of p of alpha, please write it down in the comment section. I would love to see it. For the time being, I will continue with p of alpha. Let's have a look at this mysterious function. As you can see, the function doesn't change pretty much on the upper and lower limits of the definition range. But it gets really steep right in the middle. This information might be helpful later. So far, so good. We've learned some basic theory about the TRIAC operation and found a pretty nice equation to calculate the normalized power as a function of the control angle alpha. I think we are more than ready to face our next challenge. If we want to control a real-world TRIAC, we need to generate a proper gate control signal. Since this gate control signal needs to be synchronized with the AC power supply voltage in order to switch the TRIAC on at the right moment, we need to find a way to establish such synchronization. First, let's convert the AC voltage into a square wave signal. Every rising and falling edge of this signal corresponds to a zero crossing of the AC voltage. Therefore, let's call it zero crossing signal. We now just need to detect every rising and falling edge of the zero crossing signal, wait a certain amount of time defined by the desired alpha value, and then switch on the TRIAC with a short gate pulse, which will in the end, hopefully, result in the expected output voltage across the resistive load. But how can we do all that? Well, converting the AC power supply voltage into a zero crossing signal is clearly a job we can do in hardware. However, monitoring the zero crossing signal and transforming it into a gate control signal is a task we want to do in software, especially since we later want to conveniently change the alpha value. Last but not least, we need to bring the gate control signal to the TRIAC so that it can generate the output voltage, which is also a pure hardware task. Let's focus on the software part now. Let's assume the zero crossing signal is connected to a microcontroller input. We then add an edge detection peripheral to detect each zero crossing event. Every time such an event happens, we start an internal counter. We also define a counter limit. Once the counter reaches this limit, it will stop and reset to 0. Let's also define a compare value. During counting, the counter value will be continuously compared to this value. As soon as the counter value reaches the compare value, a microcontroller output will be switched on. This pin will become our gate control output. Luckily, all these fundamental blocks and components are available in almost every microcontroller. An input with edge detection is called input capture module. A counter with counter limit is called timer module. And a counter compare value that can control an output pin is called output compare module. But how does this setup work? Let's have a look at the timing diagram. Once the input capture module detects a zero crossing event, the counter starts counting. As soon as it reaches the compare value, the output compare module will switch on the gate control output. However, the counter still keeps counting until it finally reaches the counter limit. Once this happens, the counter stops and resets to 0, which will also switch off the gate control output. On the next zero crossing event, the whole process starts all over again. The delay between the zero crossing event and the gate control signal output can now be conveniently adjusted by the compare value. We have also defined this delay as alpha. We now exactly know which components we need, so let's find them on a standard STM32 microcontroller. This is the powerful timer peripheral of an STM32F4. As you can see, this module provides a lot of inputs on the left side and even more outputs on the right side. We need to feed the zero crossing signal into an input capture input. Let's randomly select the module's channel 2 input for this purpose. We will later configure the peripheral in software to enable the green signal path. Then the slave mode controller will be able to start the timer on each detected edge on the zero crossing input. Let's use channel 1 to provide an output compare output to control the TRIAC gate, as indicated by the pink path. Good, we have successfully assigned the input capture channel 2 to the zero crossing input and the output compare channel 1 to the gate control output. However, we still don't know which microcontroller pins support these features. A quick look at the microcontroller's datasheet shows, for example, that timer 1 channel 1 can be used on pin E9 and timer 1 channel 2 is available on pin E11. Let's select these two pins. Unfortunately, most microcontroller pins support more than one alternate function. You always need to enable the function in software you want to use, otherwise the pin will not work properly. As you can see, both timer 1 channel 1 and timer 1 channel 2 are located in the alternate function group 1. That's the group we need to select on each pin, otherwise the pins won't work at all. In order to do so, we first of all need to enable the alternate function mode for both pins. Since we want to use pin E9 and E11, we need to configure the mode register bit fields 9 and 11 of GPIO port E. Last but not least, also the corresponding bit fields of the alternate function register need to be set to alternate function 1 each. So now we can configure both registers using the following C code. Don't forget to enable the GPIO port peripheral clock because otherwise the system won't work. It's also good to initialize all peripheral related registers properly, even if you don't need them or the default values already meet your requirements. We have now successfully assigned the zero crossing input to the GPIO pin E11 and selected its alternate function timer 1 channel 2. We have also assigned the gate control output to GPIO E9 and selected its alternate function timer 1 channel 1. However, up to now we have not configured the timer 1 peripheral at all. Guess what we'll do now? The first timer registers we need to initialize are the control register 1 and 2, which configure the basic timer operation like counting mode and direction. We use the slave mode control register to use an external trigger source, which is in our case the zero crossing signal that is connected to the timer input 2. Since we don't use any DMA functionality, the DMA and interrupt register can be cleared. We also clear the status register and the event generation register. The next important register is the capture compare mode register 1. Its lower 8 bits configure our gate control output compare output. Its upper 8 bits configure the zero crossing input capture input. We don't need any additional channels, so the capture compare mode register 2 can be cleared as well. Both the output compare and input capture function need to be enabled separately. This can be done in the capture compare enable register. Next, we clear the counter and set the timer prescaler to 168. Since our microcontroller is running at 168 MHz, we end up at a timer counting clock of 1 MHz. The auto reload register is very important. It defines our counter limit. Let's initialize it with 0. It will be modified later. The repetition counter register can also be cleared. The capture compare register 1 defines our compare value. Let's initialize it with 0. Channel 2 to 4 are not used, so we also clear these registers. In order to enable the main output of the output compare module, we need to configure the break and dead time register. Finally, we clear the DMA control register and skip the DMA address register. The following C function configures all discussed timer register accordingly. Don't forget to also enable the timer 1 peripheral clock. We have now fully configured the timer 1 peripheral. The auto reload register and the capture compare register 1 have been added to the timing diagram. As you can see, the capture compare register 1 directly controls the alpha value. Precisely speaking, the gate control pulse delay after the zero crossing event. The pulse duration, on the other hand, can be configured by the auto reload register. Having this in mind, we can use the following C function to conveniently adjust alpha. Unfortunately, as seen earlier, there is no function available to calculate the necessary alpha value to generate a certain normalized output power. That's why we need to use a different approach here. First of all, let's create a table that contains the resulting normalized output power values for all values of alpha from 0 to pi in 10,000 steps. We then rearrange the table and sort it by the normalized output power in 1,000 steps. Each power value exists once. Last but not least, we copy all values into a C array in order to get a nice and handy lookup table. The index of this lookup table corresponds to the output power. All entries corresponds to the necessary alpha value. Let's have a look at the plot of this lookup table alpha as a function of the normalized output power P. Comparing this plot to the earlier calculated function P of alpha clearly shows the reversed characteristics of the lookup table. Although we haven't found a closed mathematical function alpha of P, this lookup table alpha of P is a very useful and powerful utility to control a TRIAC that is connected to a resistive load. The only thing left to do is to write a C main function that gets our STM32 up and running and uses this lookup table to control the TRIAC's output power. This example code generates a normalized output power of 50%, but it can be easily adjusted to any other value. We have now successfully completed the software part of this project. But the software won't work without hardware. We still need to generate the zero crossing signal from the AC supply voltage. In addition to that, we also have to build the power stage, including the TRIAC and its driving circuit. Let's start with the gate control signal that comes from the STM32 and feed it into the base of a standard BJT. This transistor then controls an opto-TRIAC, which is connected to the main TRIAC that controls the dissipated power of the resistive load. The TRIAC and the resistive load are connected to the AC power supply. Now we need to take care of the zero crossing signal. Therefore, let's add an op-amp to the circuit that is connected to operate as a comparator. In this configuration, the op-amp will detect each zero crossing event and will generate a square wave signal on its output. Last but not least, we need to ensure that the op-amp output signal does not damage the STM32 zero crossing input pin. We achieve this by adding a blue LED and an anti-parallel Schottky diode in parallel to the op-amp output. The blue LED prevents the output voltage from rising above 3.3 volts, and the Schottky diode prevents from any negative voltages below approximately minus 200 millivolts. This is a quick and dirty solution, but it should do the job. Now we can connect the zero crossing signal to the STM32. Please keep in mind that this is only a lab bench test setup. The control circuit and the power stage share the same ground reference. I strongly recommend to use an isolated variable transformer as voltage source. It's also very helpful to use isolated differential probes whenever working with such circuits. So, here's my version of this hardware soldered on a prototype PCB. I have attached a heatsink to the TRIAC to protect it from thermal damage. I recommend to remove unused pads in the area of high voltages because otherwise the creep distance can be too small, which could result in a dangerous short circuit. We have now completed the zero crossing detection and the TRIAC power stage hardware. There's only one thing left to do. We need to find out if this circuit works or not. First of all, let's connect the TRIAC module to the STM32. Then we hook up an isolated variable transformer to the power stage. Next, we connect a resistive load and a digital power meter to the power stage output. Finally, we add 4 oscilloscope probes to the following signals. Always keep in mind your ground referenced potentials. After powering up the circuit and flashing the firmware into the microcontroller, we can see the following waveforms on the oscilloscope. As you can see, the TRIAC control signal looks fine since it triggers the TRIAC right in the center of each half wave, like it should do using the earlier discussed C code. Also, the clamping protection of this signal obviously works fine as well. The only thing that doesn't look really good is a massive voltage dip in the AC power supply voltage right after the TRIAC trigger pulse. This indicates that the variable transformer has a relatively high output impedance. So let's go back to the test setup and add a toroidal transformer as an impedance converter to the circuit. As you can see, the toroidal transformer almost completely removed the voltage dip. Next, let's measure the delay between the real zero crossing position and our zero crossing output signal. As you can see, the comparator op-amp is operating quite inaccurately, so let's adjust the voltage divider ratio as follows. This measure already almost halved the delay. Well, since this is a pure lab bench test and the op-amp already isn't our best friend anymore, let's go one step further and replace one resistor by 2 anti-parallel Schottky diodes. This again halves the delay down to approximately 75 microseconds, which should do the job. However, as earlier discussed, a delta of alpha of 2 milliseconds could cause a delta of normalized power of up to 40%. As a result, an error of approximately 75 microseconds could cause an error of normalized output power of up to 1.5%. This clearly shows that our test setup will not exceed a much higher accuracy than 1.5%. Now let's continuously change the normalized output power in steps of 4% from 0 to 100% using our microcontroller program. 100% have been calibrated to dissipate exactly 50 watts in the resistive load. This has been achieved by fine-tuning the variable transformer output voltage. Let's start the program and measure each actual output power. Now we can compare all actual and target values. As you can see, the results don't look that bad. You can clearly see the almost linear transfer function of our setup. This means that the theory, software and hardware of our setup seems to be correct. We have seen the basic theory of relation between control angle and output power using a TRIAC and a resistive load. We also managed to calculate the normalized output power for a given alpha. We saw principles on how to control a TRIAC using an STM32. We successfully found a linearization lookup table to control a TRIAC. Some hardware and software examples have been shown. Unfortunately, we didn't succeed to find a function to calculate alpha of p. We didn't carry out any further investigations to find the inconsistent accuracy of our test results. Using a comparator instead of a general-purpose op-amp is highly recommended for such applications. If possible, also use an opto-isolated zero-crossing signal. Please be very careful whenever working with mains voltage. High voltages can easily kill you. A single mistake could end your life, so please always take safety precautions whenever working with high voltages. Thank you so much for watching this video. I hope you liked it. Please let me know your comments in the comment section and see you next time.